All right, let's dive right into this explainer. Today, we're embarking on a subterranean expedition into the massive, high stakes world of drilling operations. We walk on the surface of the Earth literally every single day, but we rarely stop to think about the absolute epic engineering required to penetrate miles beneath the crust to safely and efficiently extract vital resources. It's a feat of human ingenuity that honestly rivals space exploration, but it's happening right beneath our feet. So, this brings us to the ultimate question, doesn't it? How exactly do we drill thousands of feet underground without the Earth just crushing in on our equipment? I mean, the physical stakes here are absolutely astronomical. We're dealing with intense environmental hazards, volatile gases, and literally millions of pounds of solid rock that desperately want to close up the tiny, fragile little hole we're trying so hard to create. To map out how engineers actually conquer the deep Earth, here's our game plan for today. First, we'll look at the rigs and the drilling team. Second, we'll see how they navigate high formation pressures. Third, we'll dive into fluids and directional drilling. Fourth, we'll check out casing and cementing the well. And finally, we'll wrap up with how they solve major drilling hazards. Okay, let's start our descent with Section 1, Rigs and the Drilling Team. It's kind of crazy to realize, but drilling actually begins long before a drill bit ever even touches the ground. It's this massive, heavily coordinated effort by a dedicated team. They have to dive into deep proposal planning and meticulous process mapping just to predict what they might encounter down there. And because of the sheer scale of the equipment and manpower, well, drilling economics and cost analyses are absolutely fundamental. Every single hour on a rig is incredibly expensive, so the whole shebang has to be perfectly mapped out for efficiency and safety. And the technology has to be incredibly adaptable, right? We're not just drilling in one cozy environment. We've got land rigs, which have to be transported and assembled over solid ground. But then you look at marine, offshore, and deep water rigs. These things are essentially floating cities. They're engineered to stay perfectly stable over the open ocean, while a drill string extends thousands of feet through the water column before it even reaches the seafloor. The engineering has to totally adapt to these crazy hostile surface environments. Now, no matter where the rig actually is, it relies on a few core life support systems. You've got your prime movers. These are the massive engines bringing the raw power to the site. Then there's the hoisting equipment, which handles the staggering, immense weight of lifting and lowering miles of heavy steel pipe into the earth. The rotating equipment is what physically turns the drill bit to chew through the solid rock. And finally, the circulating equipment, which we'll see is absolutely vital for pumping fluids down the hole to keep the whole operation alive. Which brings us to Section 2, navigating high formation pressures. Because as we go deeper, the physical environment really pushes back. So the really crucial thing to understand is that drilling is basically just one massive battle against pressure. First off, you have overburden pressure. That's the literal crushing weight of thousands of feet of rock just bearing down from above. Then you've got formation pore pressures, fluids and gases trapped inside the rock, desperately trying to force their way out. Sometimes crews hit abnormal pressures that deviate wildly from what they expected. And through it all, they have to carefully monitor the formation fracture gradient. That's the exact pressure point where the surrounding rock will literally crack and break apart under the stress of the drilling. Now, if those underground pressures actually overpower the pressure we're applying from above, you get what's known as a kick. A kick is when unexpected formation pressure suddenly blasts into the wellbore during drilling. Think of it like the Earth is actively fighting back against our drill bit. A kick is an incredibly visceral, urgent danger. It means highly pressurized gas or oil is aggressively shooting up the pipe right toward the surface crew. To survive this hostile environment, the crew absolutely must maintain complete well control. Everyday operations use primary control just to keep things perfectly balanced. But when a kick does happen, rapid kicks detection is a literal life or death priority, for sure. If primary control fails, they have to rely on secondary control measures and heavily specialized equipment, like blowout preventers, to physically clamp down on the well and seal it shut before that pressure ever reaches the surface. All right, let's move on to the next step and see how this builds in Section 3, Fluids and Directional Drilling. One of the most ingenious engineering solutions out there is drilling fluid, or what the industry lovingly calls mud. You've got water-based mud, oil-based mud, and even gas-based mud. And these aren't just puddles of dirty water, right? They are highly engineered chemical mixtures with very specific jobs. They control the solids, meaning they carry the drilled rock cuttings back up to the surface so the hole doesn't clog. They also manage drilling hydraulics, creating enough downward hydrostatic pressure to fight off those kicks we just talked about, all while lubricating the drill bit so it literally doesn't melt from the friction. And with those fluids keeping everything stable, engineers can pull off some seriously incredible navigational feats. I mean, we don't just drill straight down vertical wells anymore. Using advanced deflection tools, drillers can gently steer the bit to create horizontal wells, turning the pipe 90 degrees to run parallel right through a resource layer. They even do multilateral wells, creating complex, branching profiles that look almost like the roots of a tree. It totally maximizes the reach you can get from just one single surface rig. But you might be wondering, how on earth do you know where you're steering when the drill bit is literally 2 miles underground in the pitch black? Well, the answer is surveying via MWD, or measuring while drilling. This brilliant tech acts as the drill's vital GPS system. By constantly feeding geographic and depth reference data back up to the surface, the team knows the exact orientation, angle, and location of the bit in real time. It lets them hit these incredibly precise targets thousands of feet below ground. Once the hole is actually drilled, we reach Section 4, casing and cementing the well. So to make sure the immense overburden pressure doesn't just, completely collapse our freshly drilled hole, we've got to secure our progress. We do this by dropping casing down the well bore. Casing is basically heavy-duty, specific structural steel components. Engineers have to meticulously calculate heavy load considerations to make absolutely sure this casing can handle the crushing forces of the earth, plus the internal pressures of the fluids. It effectively acts as a permanent, protective steel armor for our deep earth tunnel. But here's the thing, steel casing by itself isn't quite enough. It needs to be fully fused to the rock. The process kicks off with primary cementing, where liquid cement is pumped all the way down and then forced back up the outside of the casing to lock it tight. Sometimes they have to go in and do squeeze jobs to fix specific little gaps or set plugs to isolate sections of the well. And finally, they do a job evaluation using cement bond logs. This uses acoustics to verify that the cement has flawlessly, perfectly sealed the steel casing to the surrounding rock formation. Let's move into the climax of our expedition with Section 5, solving major drilling hazards. Because despite all this brilliant engineering, things can and do go wrong. Because look, despite all this brilliant tech, the terrifying realities of the deep earth are always there. Rigs face critical, major hazards literally every day. You could get a stuck pipe, where the drill string is just wedged tight and trapped by the rock. Or maybe lost circulation, where your vital drilling fluid simply vanishes into cracks in the formation. There are severe borehole instabilities, like drilling into an unstable formation that crumbles on you, or dealing with an undergauge hole that shrinks and pinches the equipment. And of course, the ultimate threats, uncontrollable kicks that can quickly escalate into a catastrophic blowout at the surface. So how exactly do we survive all that? Well, everything we've just talked about acts as the engineered solution. To overcome these severe hazards, teams rely entirely on the careful chemistry of those specialized drilling fluids to patch up lost circulation. They rely on rigorous, flawless cementing jobs to cure those borehole instabilities, and they absolutely depend on that massive, perfectly maintained rig equipment to stop blowouts dead in their tracks. It's just a continuous, highly calculated response to the extreme dangers of the deep earth. And that brings us to the end of today's explainer, leaving us with this final, crazy thought to chew on. What other invisible engineering marvels are actively conquering the deep earth beneath our feet right now? We rarely get to see the sheer scale of the mechanics, the physics, and the on-the-fly problem-solving required to drill into the planet like this. It truly is a high-stakes world hidden just out of sight. I really hope this breakdown helped illuminate exactly what happens out there on the rigs. Thanks so much for joining me on this deep dive, and keep asking the big questions. Welcome to today's explainer. We're going to be looking at something truly monumental. When you think of oil and gas drilling, you probably just picture a giant drill bit spinning in the dirt, right? But the reality, well, it's so much bigger than that. We're talking about a literal astronomical mega project. It's a world where highly specialized teams use massive, cutting-edge technology to completely conquer some of the most hostile underground environments on the planet. So today, we're unpacking the absolute foundations of drilling engineering and field development planning, showing you how a complex, invisible geological blueprint transforms into a living, breathing reality. Okay, let's dive straight into this. To understand how a well goes from just an idea to the actual bottom line, we're going to deconstruct this massive undertaking into 4 main pillars. First up, the master plan. Then we'll meet the human engine driving the whole operation.
After that, we'll construct the anatomy of a well, and finally, we'll break down the crazy economics behind this multi-million-dollar bet.
All right, Section 1, the master plan. This takes us all the way from raw seismic data to the final abandonment of the well.
So, right off the bat, you've got to realize this is not a quick operation. The life cycle of a field spans literally decades. And long before a drill bit ever touches the dirt, there's this massive scouting exercise. Exploration geophysicists are out there analyzing seismic data, studying the regional geology, and weighing potential costs against oil prices. It's a highly calculated leap of faith. It all kicks off with exploration, where the only goal is to figure out if hydrocarbons are actually down there. If they hit something, we move to appraisal. That means drilling more wells just to map out the exact size and depth of the reservoir. Once they know it's a moneymaker, we hit the development phase. That's drilling the actual development wells and building the production facilities. Fast forward through years of producing oil, and we enter intervention and maintenance. Here, teams might stimulate zones, by fracturing or acidizing, just to optimize the flow. And finally, every single field reaches abandonment. When it costs more to run than it makes, the wells have to be safely plugged and surface facilities removed. The wild part? Every single phase completely relies on the success of the one before it.
Okay, moving on to Section 2, the human engine, the specialized drilling crew.
Because listen, all of this incredible engineering, this master plan we just talked about, it's absolutely nothing without the people. We're talking about the tactical team executing the plan on the ground. And the way this works is actually a really fascinating contracting triad. First, you've got the operating companies. They own the lease and manage the big picture vision. But here's the kicker. They usually don't drill the well themselves. Nope, they hire drilling contractors. These guys own the rig and employ the crew, and they're typically hired on a strict day rate to drill the hole to exact specs. And lastly, you have the service companies. These are the ultra specialists brought in for very specific tasks, like well logging or surveying. Now, what's really interesting here is the chain of command, because operating a rig requires insane physical endurance and absolute discipline. At the very top, you've got the company man. They're the operator's rep, calling the big shots. Then there's the tool pusher, the contractor's rep, who oversees everything happening on the rig floor. Under them is the driller, who operates the actual drilling machinery. But get this, consider the derrick man. This person works on what's called the monkey board. It's a tiny platform hanging 90 feet up in the air, handling the upper end of the drill pipe. 90 feet. And back down on the floor, you've got the roughnecks. They handle these massive wrenches called tongs to screw and unscrew individual lengths of heavy pipe. It is literally an awe-inspiring orchestra of heavy machinery and human grit.
All right, let's pick up the tempo. Section 3, the anatomy of a well, where we physically build this underground fortress. When we talk about drilling a well, we aren't just digging a big hole in the ground. We are constructing an impenetrable, telescoping shield straight down into the earth. And the drilling engineer designing this fortress, they are governed by 3 strict absolute rules. Rule number 1, drill safely, period. Health, safety, and environmental considerations, HSE, they supersede absolutely everything. This is a non-negotiable reality. Safety comes first, even if it means totally changing plans, delaying operations, or eating massive extra costs. The second rule is to provide a fit-for-use well, which basically means making sure the borehole and the producing formations aren't damaged. And third, and notice this is last, only after safety and usability are totally locked down, the goal is to minimize the overall well cost. Let's move to see how this builds out step by step. Wells are constructed using concentric strings of steel casing. Think of it like a massive telescope extending downwards. Step 1 is the conductor pipe. We're talking a gigantic 30-inch or 26-inch steel pipe, driven about 100 feet down with a literal pile driver. This stops the loose surface dirt from just caving in on itself. Step 2 goes deeper, drilling an open hole to install the surface casing. Then step 3 pushes even further to set an intermediate casing, which basically seals off any tricky or problematic formations. Finally, step 4 is the production casing. This is run down and cemented in place to perfectly isolate the oil-producing zone, which we call the pay zone. Actually, let's pause for a second, because I really want to focus on step 2, that surface casing. This 13 3/8-inch steel pipe is drilled down through the near surface to about 2,000 feet. And its primary job, to protect potable drinking aquifers. It acts as this absolutely critical environmental shield. It guarantees that no matter what crazy stuff is happening deeper down in the well, local drinking water supplies stay completely untouched and totally safe. It's a perfect, tangible example of why those HSE safety rules supersede everything else. Which brings us to our final pillar, Section 4, the multi-million-dollar bet. Drilling economics. Everything we've talked about so far, the specialized crews, the thousands of feet of steel casing, the decades of planning, it all requires capital. Staggering amounts of capital. So before a drilling program even gets a green light, it needs an authorization for expenditure, or AFE. This is essentially the master budget. And drilling economics? They are wildly complex. The costs are broken down into a few distinct categories. First, you've got time-related costs. This includes the daily rate of the rig, transport, food, accommodation. Literally every single second that rig is active, the meter is running. Then you have depth-related costs, meaning the deeper you drill, the more casing and cement you have to buy. And finally, fixed costs, like the actual wellhead equipment. So, the crucial point is, that ticking clock is expensive. To put this into perspective, a standard land rig might run you about $20,000 a day, but a specialized offshore jackup rig, that can cost $72,000 per day just to have the rig operational. No way, right? But that's exactly why the tool pusher, the driller, the roughnecks, why the entire crew has to operate with absolute, flawless efficiency. Any delay from a broken tool or a logistical mess instantly equals massive financial losses. And it's not just the type of rig. Geography plays a huge role in swinging these budgets. An offshore well on the west coast of Africa can cost up to 30 times more than an average onshore well in the United States. 30 times! Drilling is by far the most expensive part of the whole exploration and development process. That rigorous efficiency we talked about, it's not a nice to have, it's an absolute necessity. But the AFE isn't just about where you are on the map. It's about the physical reality of the earth beneath you. Are you drilling an exploration wildcat well in totally uncharted territory, or a development well in a reservoir you already know? What are the subsurface conditions like? Are you dealing with high-pressure, high-temperature zones, or maybe highly corrosive sour gas? Trust me, hitting a sour gas well completely changes the metallurgical requirements of your steel casing. It dramatically escalates both the financial and the physical risk profile of the whole project. Every single variable multiplies the stakes. Ultimately, this all loops back to the core philosophy of the drilling team. Every single well is a multi-million-dollar mega project that relies on this huge team of specialists. But at the end of the day, their priorities are crystal clear. Maintain well integrity, avoid hurting anyone, and deliver the well on time and in budget. It's this continuous, incredibly delicate balancing act of protecting human life and the environment, all while managing some pretty extreme financial costs. So, what does this all mean for the future? We've looked at the telescoping steel, those massive daily rig rates, and the derrick man working 90 feet up in the air. But as we keep pushing the limits of technology to drill deeper, faster, and into way more hostile underground environments, how will the human element, those crucial roles on the rig floor, evolve to manage these truly astronomical risks? It's a fascinating frontier to think about. Thanks for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.
Welcome to the quiz section, Fastest Finger Edition.
Okay, let's dive right into this. Welcome to the Explainer. Today, we're not just looking at massive hunks of steel and machinery. We're going to dissect drilling rigs as if they were highly engineered, interconnected organisms. You know, these giants of modern engineering, they're really complex, breathing systems, and to truly grasp how we extract resources from deep within the earth, we've absolutely got to understand their anatomy. Here's the blueprint for the Explainer today. We'll be breaking down this massive machine systematically, sizing up the rig, hoisting system mechanics, rotary systems explained, the circulating system, and finally, specialized offshore systems. Let's get to it. First up, Section 1, Sizing Up the Rig, the genetics of the operation. So this is the very first and honestly absolutely crucial step of the drilling process. The stakes here are astronomical.
I mean, get the rig selection wrong right out of the gate, and you aren't just facing minor delays. No way. You're looking at severe formation damage from poor solids control, abysmally low penetration rates, and literally massive cost overruns. It's all about building the exact right DNA for the specific job. Back in the day, rig selection was often as simple as looking at a basic depth rating. You needed to drill a 5,500-meter prospect, well, you just grab a 6,000-meter rig and call it a day. But that's an outdated practice now. Today, modern engineering dictates that a 6,000-meter rig must match the exact rigors of the specific well design. Some rigs just can't handle the physical or technical demands of a complex modern well, even if they have the right tape measure length. To avoid a multi-million-dollar mismatch, engineers use a really methodical 5-step procedure to start a project from scratch. Step 1, design the well. Step 2, establish the maximum expected loads for drilling, testing, and completions. Step 3, scan the area to find available rigs that actually match those intense requirements. Step 4, discuss availability with the rig contractors. And finally, Step 5, issue tenders and select the rig based on a really delicate balance of cost, capability, and availability. It's a rigorous matching game, for sure. Now, when weighing that final decision, several specific criteria come into play. We look at the well objective. Is it a wildcat exploratory well or an appraisal well? We calculate casing loads, target depths, rotary speeds, and environmental conditions. So the crucial point is that a rig is only as good as its physical capabilities and the manpower running it. You could have the most advanced hardware on the planet, but if the personnel lack the experience, the training, and a flawless safety record, the entire operation is just a massive liability.
Moving on to Section 2, hoisting system mechanics, the skeleton and muscles. Okay, now that we've genetically selected our rig, let's look at its physical structure. The hoisting system is the literal heavy lifter of the operation. It's responsible for holding, lifting, and lowering all the massive equipment required to drill, complete, and intervene in a well. The foundation of this whole system is the substructure and the derrick. Depending on the rig's size, the substructure sits anywhere from 10 to 35 feet high. It is incredibly over-engineered and rated to hold immense setups of pipe and the crushing load of the heaviest casing runs. Mounted directly on top of this is the derrick, that iconic tall steel tower. Its primary function? Well, it provides ample space and the absolutely crucial vertical height required to hoist incredibly long sections of pipe into the well, all while withstanding immense compressive forces and howling wind loads.
But you might be wondering, how do human operators actually manipulate hundreds of thousands of pounds of steel? The answer relies heavily on mechanical advantage, achieved through the block and tackle system. This is a brilliant arrangement of the traveling block, the stationary crown block at the very top of the derrick, and the heavily spooled drilling line. It basically acts as a force multiplier, making it possible to handle these otherwise impossible loads safely and efficiently. Working in perfect concert with the block and tackle are the rig's other powerful muscles. The drawworks, which actively reel the heavy drilling line in and out. The immense drums, the elevators that securely grip the pipe, and of course, the heavy-duty hooks. Together, these components ensure the smooth, powerful, and controlled vertical movement of the entire drill string. All right, Section 3, Rotary Systems Explained, Spinning the Bit. So we've seen how the rig lifts, right? But actually, drilling a hole requires crushing through solid rock. Down in what we might call the digestive tract of the rig, we generally use one of two distinct rotary systems to actually spin that bit, the conventional Kelly system and the top drive system. Now, the conventional setup uses a rotary table on the rig floor and a hexagonal piece of pipe called the Kelly to apply rotational torque to the drill string. It's your classic traditional method. But the modern alternative is the top drive, where a hydraulic or electrical motor is actually suspended high up in the mast of the rig itself, driving the rotation from above. And this brilliantly illustrates how modern engineering streamlines a really complex process. Because the motor is suspended, the top drive system entirely eliminates the need for the Kelly bushing, or the master bushing down on the rig floor. It acts directly as both the rotational driver and the primary conduit for our drilling fluids. Some even feature pull-down chains that utilize the rig's own weight to physically push the bit down during shallow drilling. It's just an incredibly elegant and efficient evolution in design. That brings us to Section 4, the circulating system, the pulse of the rig. Just as blood circulates through our veins, drilling fluid, or mud, needs to flow from the surface to the bottom of the hole and back. To push that incredibly thick fluid miles deep into the earth, you need serious power. As the source material explicitly states, mud pumps are considered as the heart of the drilling fluid's hydraulics. And honestly, this exact quote anchors our whole anatomy of a giant metaphor perfectly. Without these massive mechanical hearts pumping continuously, clearing cuttings and controlling pressure, the entire drilling operation would just flatline instantly. Let's take a quick look at the specs of these mechanical hearts. A typical rig utilizes 2 to 3 massive reciprocating positive displacement pumps, and they primarily fall into 2 categories: duplex and triplex pumps. A duplex pump has 2 liners and is double acting, meaning it actively moves fluid on both the forward and backward strokes. A triplex pump, on the other hand, utilizes 3 liners but is single acting, moving fluid only on the forward stroke. Now, while the pumps act as the heart, the rig also has a highly advanced nervous system. Data acquisition is the functional pulse of the drilling process. Using advanced computing systems and downhole measuring devices like logging while drilling, or LWD, and measurement while drilling, or MWD, operators can instantly retrieve and monitor trends. This constant stream of data is a game changer. It allows them to detect downhole problems immediately, adjusting the rig's functions completely on the fly.
Finally, Section 5, Specialized Offshore Systems, Testing in Extreme Environments.
We've explored the anatomy of a standard rig, but what happens when we plunge this giant steel organism into the ocean? I want you to think about this for a second. How do you drill a perfectly precise hole, potentially miles deep into the seabed, when the massive rig you're operating is constantly floating, shifting, and moving around on the ocean surface? The staggering physics and subsea engineering required to solve this problem is it's nothing short of awe-inspiring.
The first critical solution is the marine drilling riser. Think of this as a vital steel umbilical cord. It's a direct extension of the wellbore that stretches all the way from the mudline down on the seafloor, up through the water column to the derrick floor on the floating vessel. It serves a vital dual purpose, safely guiding the spinning drill string down into the earth and providing a closed loop to return those essential drilling fluids and rock cuttings back up to the surface. But here's the catch. A riser is completely useless if the ship drifts away. Enter the Dynamic Positioning System, or DPS. Rigs like the Pacific Sirocco, the West Jupiter, or the Stena AB aren't just dropping anchors, they are actively flying in the water. The DPS utilizes environmental sensors and heading references to constantly note wind and wave fluctuations. Its control system then instantly sends signals to massive thrusters and propulsion units scattered around the hull, actively fighting the ocean to keep the rig locked onto an exact, unwavering geographical coordinate. Even if the rig maintains its exact GPS coordinates, it is still physically bobbing up and down on the ocean waves, a vertical motion called heave. To prevent the drill bit from smashing into the rock below and then lifting off completely, engineers use motion compensation systems. These act as gigantic, highly responsive shock absorbers. They limit the vertical excursion of the floating unit, perfectly nullifying the effects of the vessel's heave. This ensures the drill bit stays planted with consistent weight, completely isolated from the ship riding the ocean swells far above it. It's brilliant. And let me tell you, the environment does not make this easy. The offshore stakes are incredibly high. Engineers must constantly battle the immense, relentless energy of the ocean, which is literally trying to tear that riser apart. They have to design systems to conquer vortex-induced vibration from deep ocean currents, flow-induced vibration from the powerful fluids pumping inside, and the compounding, relentless damage of wave fatigue. It's basically a constant mechanical war against nature. Which brings us to our final thought. Considering the incredible forces of wave fatigue, deep ocean currents, and massive vessel heave, the fact that we can maintain a stationary, spinning drill bit from a rocking vessel in the middle of a turbulent sea is an absolute triumph of human engineering. So I'll leave you with this. As our world's energy needs continue to grow, how much further can we push the incredible limits of subsea engineering to master the ocean? Thank you so much for exploring the anatomy of these steel giants with us today.
Welcome to the quiz section, Fastest Finger Edition.